So when you arrive in lab this week, this is what you'll see. We have here a breadboard that contains a number of components. Over here in this portion of the board is what's called a 555 timer. That's what this integrated circuit is right here. Now the 555 timer has a huge number of different applications and it's an extremely powerful chip, but for today all you need to know is that we're using this chip to generate the clock signal. If I apply power to the board here, you can see that this LED lights up, but it's going to oscillate now with a 50% duty cycle of about 1 second. That is going to represent the clock signal that's being generated by this 555 timer. What you're going to want to do to connect the clock signal is you're going to want to connect right to this point here. You're going to want to connect to the pin 3 of the 555 timer. That's going to give you the clock signal. That connection is going to need to go to pin 1 of this first chip, and it's also going to need to go to pin 5 of this first chip. So pin 1 and pin 5, you can sort of daisy chain them from here to pin 1 and then from pin 1 to pin 5. And so that's the first thing that you need to know. The second thing is that I have a push button switch that's wired here, and that push button switch is going to be our reset. You can see here that I have the resistor going from power into the push button, and then from the other side of the push button to ground. So we kind of have a complete circuit right here that's going between power through a resistor and to ground. You'll remember that we always take our signal off between the resistor and the switch, so that's what's happening right here. That's going to pin 2, and then pin 2 is also going to pin 6. And then for a future application, this green wire, which you don't need today, is also going to provide an asynchronous reset to the first flip-flop of this device as well. Speaking of it, here we have our first chip. This is a 7473, and that 7473 is a negative edge-triggered JK flip-flop with an asynchronous reset, an asynchronous clear bar. It actually contains 2 flip-flops. The first is sort of in the left half of the device, and the second is in the right half of the device. So this chip contains 2 flip-flops. That's all you're going to need for today's lab. This one breadboard will also serve us for the next lab, and so here we have a second 7473, which offers 2 more flip-flops. So we'll need a total of 3 flip-flops for the next lab, but for today we're just going to need this one chip. So this chip will be completely unused. As a matter of fact, all of the other chips here are also going to be completely unused. Those are strictly, this is an AND gate, and an OR gate. Those will be useful for next time's lab, but for today they're not going to be essential. So you can see here that we have the power and ground already made. So here this is a power connection, and up here this is a ground connection. It's unusual. One thing unusual is that I've made the connections over here. Let me show you. Here are the connections that are coming from the power supply. Ground is going to here, and power is going to here. So I've hardwired the top red lead and the bottom blue lead, but then I've also added 2 wires. This wire right here transitions the ground connection so that it's also on the top, and this wire right here transfers the power connection so that it's also on the bottom. I did that because these flip-flops take their power from sort of the quote-unquote wrong side. So the power comes off the bottom and the ground comes off the top. It's just the way that the chips were designed. There's nothing we can do to change that, so I've made it available on both sides so as to minimize the wiring necessary. It's also helpful in places like over here where I had the switch that needed access to both power and ground on the same side, and the 555 timer also needed access to both power and ground. So you're going to have 3 tasks. First of all, you're going to need to connect the clocks, and so you're going to need 2 wires to connect the 2 clocks here. You're going to need to connect the 4 inputs, the J sub A, J sub B, K sub A, and K sub B. So you'll need to connect those to the appropriate places, and they'll all be internal here. So it'll either be plus 5 volts, 0 volts, or it'll be from one of the signals that's currently on this chip. And then you're also going to need to take the Q sub B and the Q sub A, and you're going to need to route them over to these 2 LEDs. I'm just going to use these 2 LEDs right here, the 2 on the right. Don't need the third one today. We'll need it for next time, but for right now we're just going to use these 2 LEDs to represent those. So a simple wire coming in and connecting up here, for example, will give you what you need to make that connection. Obviously this LED goes through this resistor to ground, so if you connect 5 volts up here, the LED will light. If you connect 0 volts up there, the LED won't light. And here's what the circuit looks like when it's been wired up to do the first circuit. You can see here that I've connected these two LEDs to the first flip-flop chip over here. There's actually several chips here that are not being used for this particular example. So you don't need to worry about those. That'll be for future work. But we're using two flip-flops, both contained on this first chip here, and they're driving these two LEDs. You'll notice then that I've made connections over here between the 555 timer for the clock signal. That has to go to the clock for the first two flip-flops here. And so that's successfully being transmitted to the first two flip-flops. And I've got these connections. Then these other connections are just connecting the J sub A, J sub B, K sub B, and K sub A to the appropriate places. So you can see that it is in fact generating a particular sequence, and it is the sequence that I calculated according to my analysis. The only other thing that I wanted to demonstrate is that we can use the reset button here, and it's an asynchronous reset. So you'll notice, for example, that the clock signal is going high and then low. Every time that it goes low, we see a transition in the state of the device. But the reset button doesn't care about that. It will reset it regardless of whether or not it's on an active edge or if it's in the middle of a particular cycle. So I can do it right now, and that was not on a particular active edge. So it's just good to know that the reset button will reset at any point in the cycle. It doesn't have to be on the active edge. And this is what the circuit looks like when I've rewired it for the second problem. We're getting a different pattern of lights here. If you really paid attention, you would know what that pattern of lights was representing. It's a particular and slightly interesting pattern. But it's still a pattern of 4 different states. Of course, 2 flip-flops can only have 2 to the second or 4 different states, and we're seeing what those states are. Remember that these are reflecting Q sub B and Q sub A on these 2 LEDs right here. So Q sub B and Q sub A are cycling through the 4 possible combinations of those 2 flip-flops. And you should verify that these in fact match the pattern of ones and zeros that you had analyzed in the original circuit analysis.